Hey guys, let's prove that this function is continuous using epsilon and delta. Okay, before we fill in the details, let's see a picture and see what we're talking about. So we're talking about this parabola here, and we're trying to check that it's continuous at the point 3, 7. Now, what the delta epsilon definition of continuity says is that if your inputs are really close to 3, then your output should be really close to 7. And the way it works is almost like a game. We say, well, okay, how close would you like the outputs to be to 7? And if someone said, oh, within 0.5, so they could go up to 7.5 or they could go down to 6.5, what I would do is I would say, oh, well, I promise you that as long as the inputs are within 3 points, I guess we have to zoom out to see what they are, but as long as those inputs are between 3.09 and 2.91, then if we zoom up here, we're going to see that the outputs are absolutely going to be in that red region. Now, my zooming around was a little fun, but I hope you can see that the point is that to show that we're really getting arbitrarily close to 7 and we're staying close to 7, all we have to do is show that no matter what we set this red tolerance to, even if we make it very small, there's a way to ensure that if our inputs are sufficiently close to 3, then our outputs are going to be at least that close to 7. And so let's go back and see how we're going to write this up with a proof. So, by the way, I think I forgot to write plus there. Okay, so I've color-coded things, and in a real analysis proof like this, they basically all have the same format. So we want to show that no matter what red tolerance we take, that's our red epsilon, we're going to be able to find a green horizontal tolerance so that if our inputs are within that green strip, okay, so this is measuring x values, then our outputs are going to be within this red strip here. And if you think about these are y values, and that's why we're measuring in the y direction. And so how do we fill in all the details? Well, my job is to tell you what delta has to be equal to. And as long as I can make a delta that works, then we win, right? There's no bonus in math for finding the best delta or the prettiest delta. As long as we find one that works, we win. And in fact, for the reader's convenience, we might try to choose a delta that is maybe not necessarily the absolute, theoretical best, but one that's going to help the reader understand what's going on. And so the way I like to have my students work on these proofs is to think about ultimately what it is we're going to need to prove. Ultimately, we're going to have to simplify the f of x minus f of 3. And so let's work out what that is. So f of x is, of course, we have a formula for it, x squared minus 2x plus 4. F of 3, if we plug in 3, I think we get the number 7. And if we keep simplifying a little bit, move that down there, we in fact get x squared minus 2x minus 3, which I'm just going to continue this down below. This is going to factor as x minus 3 times x plus 1. And if you notice, this factor here is something that we are already in our proof. Once it's complete, we're going to know some information about. We're going to know that x minus 3 in absolute value is strictly less than delta. And so let's do that. We may as well fill that in right now. Whatever this product is, it's definitely less than delta times the absolute value of x plus 1. Now, this is where our proof really starts to get interesting, because what students might want to do the first time you see one of these proofs is you might like to let delta equal epsilon divided by x plus 1. I'm going to put big warning flags around this. This is not what we're going to do. But I want you to see why students would think that this might actually make sense. For instance, if we were able to do that, then we could just take this delta, say it was equal to epsilon over x plus 1 multiply by x plus 1. And then once we simplify, we would just get an epsilon. And so sure enough, we showed that the thing we wanted was less than epsilon. The problem is that delta needs to be a number. And at the moment, we've written something depending on x. And x isn't even defined, right? X is just some letter or some like dummy variable for our function. So this absolutely is not allowed. But let me show you how we can remedy this. So when you think about what is happening here, remember, we're in charge. We get to decide what our delta is. And I am going to decide for sure that delta is less than or equal to 1. Right? If at the end of the day, I'm just going to guarantee that it's smaller than 1. I'm just going to force it to be true. I get to declare it. And if we know that, then that means that x has to be between 4 and 2. Right? So if delta is our tolerance left and right, and we're saying, hey, I promise you I will never let you go more than 1 unit to the left or 1 unit to the right, that is guaranteeing that x is between 2 and 4. And that is going to mean that x plus 1 has got to be between 5 and 3. And so that factor down here that we were, we were kind of looking at, well, absolute value of x plus 1 is some number, but some number between 3 and 5. And so no matter what it is, this will be less than or equal to delta times 5. Maybe I'll kind of put that in a little box there to indicate where that's coming from. Or maybe I should just make this a blue 5. And so now we see that the thing we're trying to show is less than epsilon. We've so far shown it's less than something that is less than or equal to 5 delta. And so if we go back and we say, let's make sure that delta is also less than or equal to epsilon over 5, well, if we could have both of those things true, then that would make this thing, we would be able to say this is less than or equal to epsilon over 5 times 5. And of course, that is going to equal epsilon, which was our goal. And so we're basically done. All we have to do now is tidy up this thing up here. So how on earth do I make a delta that, how do I guarantee that it's less than or equal to 1 and also less than or equal to epsilon over 5? Well, the easiest way to do that is just to take the minimum of those two numbers. And so I'm going to replace this orange box, and I'm going to just write delta to be the minimum of 1 and epsilon over 5. So now delta, it's the smaller of those two numbers, so it's going to be less than or equal to 1, and it's going to be less than or equal to epsilon over 5. And now our whole proof will work. And so now to finish it off, let's have some fun, and let's go to Desmos and see if our formula actually works. So if I let delta be that formula that we just typed, let's type the minimum, parentheses, 1, comma, and then the other one was e divided by 5. And so when I type that in, so now this should adaptively change as our epsilon changes. And so at least for all of the ones I'm showing here, that green strip definitely keeps our graph inside that red region. And even if I were to make my epsilon bigger, because that's, I think, where things can kind of go a little haywire, you'll notice that at some points, if epsilon over 5 is bigger than 1, our strip doesn't get any wider, but no matter. Our proof is still working, and we get to see it in action.